Okay, so today is kind of our last day of multi-component phase equilibrium before we transition into chemical reaction equilibrium and then close the door on classical thermo. So what we've hopefully covered in a little bit over half a semester is basically everything that you hopefully would have learned in a second semester undergrad chemistry class, hopefully in greater detail and rigor than you would have received previously from your undergrad institution. So what we'll start off with is a recap. Recap of phase equilibrium. Specifically, we spent a decent amount of time yesterday looking at graphs of the Gibbs free energy that looked sort of something like this. And it's important to really understand kind of the functionality and the curvature of some of these plots because we can learn a lot what's going on. In this particular drawing, we see that we have these inflection points here where the curvature of the Gibbs free energy in this case is negative, so it's less than 0, which means this is unstable. Right, so obviously this region is sort of, you can never really truly exist in there. So that we know if we ever form a region like this here, where the Gibbs free energy is concave, we know that there's some mixture composition that's not going to be soluble. Now mathematically, we have the governing liquid-liquid equilibrium equation. Right? We can always rely on this particular equation to help us solve any of the problems. But a better intuitive understanding of sort of how multi-component phase equilibrium works kind of comes out of looking at these graphs and kind of really sort of intuitively understanding why they behave in certain ways. So what's really interesting, though, about multi-component phase equilibrium is that fundamentally it's stuff that we kind of all take for granted, but it does kind of produce some sort of non-intuitive conclusions. For example, so gases dissolving into liquids, right? If you really think about that fundamentally, you have a supercritical fluid who then is now behaving more like a liquid. That can only be possible in a multi-component system. Or in the case of even water evaporating, you're taking a liquid that is well below its saturation conditions and you're causing it to be in the gas state. Likewise, solids dissolving in liquids. Really what you're doing in a multi-component system is you're taking a pure component that doesn't want to behave in a particular way and you're providing it a mixture composition where it can behave vastly different. And that's really kind of the interesting part. Okay, so what we talked about is that for an ideal mixture, the delta mixing of the Gibbs free energy is always less than 0. And no matter what, everything will always be miscible. What we want to talk about is under all circumstances, let's say we don't truly have an ideal mixture. Let's look a little bit about why I've made the statement that no matter what happens, a small amount of one material can always dissolve in another. And that has to come down to this region of the Gibbs free energy plot. No matter what happens, at dilute amounts of either x1 and x2 or x2 and x1, you're always going to have a decrease in the Gibbs free energy. I think it's useful to take a little bit of time, take a look at why that's the case, and sort of theoretically understand that, yes, everything has to be miscible and everything else, at least to some extent. So what we're going to do is we are going to come up with sort of a simplified system to manipulate mathematically to investigate this. So what we'll say is that we have ideal S mixing and non-ideal enthalpy of mixing, just as a demonstration. So if we look at the total Gibbs free energy of the mixture, the same thing that we kind of have plotted up here, it's equal to the enthalpy of the mixture and for this, we're going to say that our reference states are the pure species of whatever temperature and pressure they are. So we could just say this is 25 degrees C in 1 atmosphere. We're saying that's our reference state. That's our reference state for component 1. That's our reference state for component 2. But it could be any arbitrary temperature and pressure, right? We get to define that. So in this case here, this is also the delta G of mixing, and then this would be the delta H of mixing, and this term here is the delta S. In this case, it's an ideal mixture. Those are the simplifications we're making for this particular instance. So if we had assumed that it was an ideal enthalpy of mixing, right, then the Gibbs free energy would simply just be the delta S of mixing, and we would have the scenario where everything is miscible. Now, I don't necessarily want to get into a habit of making it seem like the only thing interesting happening in mixtures is the enthalpy of mixing, right? Entropy doesn't always necessarily 100% promote mixing, right? You can have positive excess entropy of mixing. Generally speaking, that's not the case, right? Generally speaking, the enthalpy is the reason why things aren't going to be miscible. But there's a little exercise that I like to kind of run through with the delta S of mixing. So let's look at, it's actually a bit of a tangent, but I like this idea. The excess entropy of mixing being less than 0. So if I had to visualize negative excess entropy of mixing, right, that would essentially mean that the entropy of a actual mixture is going to be less than the entropy of an ideal mixture. Does that make sense? So what we're looking at with the excess property is what is its deviation from ideal mixing behaviors. So can someone conceptually describe to me how we would have less entropy of mixing than ideal entropy of mixing?
Basically, I'm thinking is like, say you had, let's assume like the temperature doesn't change. It'd be like you put a gas in there, and by mixing these two gases together, you end up forming a liquid. So you get less disorder.
Sort of. The less disorder. You're on the right track with the less disorder. Let's draw out 3 diagrams here. So in this case here, the S of the mixture is less than the S of the ideal mixture. We'll draw out a middle one here, where we have the excess entropy is equal to 0, so in which case your S of the mixture is equal to the S of the ideal mixture. And then lastly, we'll finish off with the third box, where the excess entropy of mixing is greater than 0, where S of the mixture is greater than S of the ideal mixture. Okay, now remember, the entropy of an ideal mixture was calculated based on the ideal gas law and random mixing. Right, so in the case of an ideal gas, molecules of type A, molecules of type B, they have no idea where anyone else is. So it is a total random mixture. Everything just goes wherever it wants to. There's no correlation in positions. It is basically just a total random system. So if I were to reach my hand at any point in any position and grab a molecule, who knows what I would get? Right? It would just be proportional to the mole fraction. So that is no excess entropy of mixing. This is ideal entropy of mixing. So if I were to redraw this system for a negative excess entropy of mixing, so that there's less mixing than the ideal case, what would it look like? How should I redraw these red and...
They would be more close together, like they would be...
Exactly.
Two reds or three reds.
We would have maybe some regions here that we'd have, you know, preferential organization of one type around another. Right? It's still a multi-component phase, right? So there's still mixing on a macroscopic level. But this totally makes intuitive sense, right? We have less than ideal mixing. So this is a perfect scenario of something, let's say, like water and ethanol. Ethanol is what we call a hydrotrope. It's not quite an amphiphilic molecule, right, where you have a organic region, right, the CH3, CH2 groups, and you have an OH and alcohol. Right, so it makes sense that maybe the OH of the ethanol interacts a little bit with the water, but those hydrocarbon components, they kind of want to isolate themselves a little bit. This is a system that has a negative excess entropy of mixing. So here's my question for you guys then. What is positive excess entropy of mixing? How can you have more mixing than complete random mixing? Nope, these are all mixed at the same temperature, same pressure. What's that? One more time, I'm sorry, I couldn't hear you. So it has to be more, they're perfectly miscible, right? But they have more entropy being generated than as if you had a total random mixture. So let's say it's a 50-50 mixture in all circumstances. There are mixtures that have positive excess entropy.
Do some of them, like, in the past now, not necessarily a phase, like, you can sort of separately change in small amounts, but not.
Kind of. It actually looks very similar to this scenario here, but different. So it's easiest to describe positive excess entropy of mixing in two different ways. I'm going to draw out two different scenarios, and we can determine which of these two are going to necessarily have positive excess entropy of mixing or not. I'm going to say that we have, let's see, how do I want to draw this? Rod-like molecules. So if I have, not spherical ones, but let's say big, flat molecules. Now I drew this one out to be somewhat random. If I were to then, let's say, draw it out rather like this, which of these two do we think would have more entropy? It's actually the one on the bottom. You can't really tell based on how I drew it. You have to put some math associated with this, right? But anyway, let me conceptually tell you why this is a thing. So entropy sometimes is viewed as total randomness, right? But that's not strictly true. It's deceptive. We may look at this top system here and think, oh my goodness, everything is totally random. But if you've got, let's imagine you've got these really long sticks and you throw them into a box, right? They'll jam up against one another. and they won't be able to move. So for example, right, maybe this molecule here, right, it doesn't have that much to move around. So it's kind of locked into position. So if you can imagine then, if you sacrifice a few molecules to be sort of sticking together, that gives your other molecules a lot more move to wiggle around in. So the interesting thing about entropy, and this is really kind of a counterintuitive thing that's starting to become a hip research topic, is that entropy induces order, but it's deceptive. We are inducing order at some regions to get more disorder at other regions. So it can be slightly deceptive just to look at this and say, oh, well, clearly one's more organized and has less entropy. But if you look at the collective phase behavior of the whole system, it's really clear that the bottom one is actually going to do better. So the interesting thing is the only system where you have no structure induced with entropy is if you have totally random ideal mixing. But if you do have negative excess entropy of mixing, that means the two molecules really don't like each other that much and they'll stick together and they'll associate more. But you can also have structure induced by positive excess entropy of mixing. So the notion that entropy just is randomness is sort of a bit misconstrued. Yes?
Does that have something to do with the fact that, like, when you induce the structure over there, now these rods can, like, rotate where they couldn't up here, and in the ones over here where you have the small molecules, like, they're identical if they rotate, so they don't really have a lot of inertia.
Bingo. So basically, yes. It is in a scenario over here, right, where we have negative excess entropy of mixing. This is where we have sort of compositionally dissimilar molecules. Ethanol, water isopropyl alcohol, right? Benzene, cyclohexane, that's pretty ideal. Sorry, cyclohexane ethanol, like what we did in the homework. In this one over here, it's shape mismatch. So there's some computer simulations that are coming out in the past 5 years or so that show that if you have a system of hard particles, which we'll talk a little bit more about in StatMech, but basically there's no interparticle interactions, that means all of their phase behavior is determined on their shape, which means that all of the phase behavior is determined strictly based on entropy. And in those scenarios, the only thing that matters is the shape of the molecule, not what kind of polar groups and all that stuff has. So this right here is all sort of the forgotten area of thermodynamics. Because for the most part, you and I, water's pretty important to us, right? So water is the solvent that most everything is used for daily life. But in terms of organic systems, they're not very strongly interacting. So the shape of organic molecules actually has much more of an impact. So it's easy to forget the role that entropy plays in phase behavior. It's not just ideal mixing. So now researchers are becoming much more in tune of how the shape of the molecule is really ultimately affecting its overall behavior. It's enough for in aqueous systems to push things left or right, but in the case of organic systems, the shape of the molecules can almost become more important than their functional groups. And the shape is what determines oftentimes the entropy of mixing. Which is a little side tangent. But I think it's really interesting to think about, right? And this one plagued me for a really long time. How can you have more mixing than complete random mixing? And in fact, if you mathematically were to assess the entropy of this system, it does have more entropy, right? But you have to induce some structure to get more randomness. The other analogy that I like to use is imagine you've got a bunch of children playing around in a gymnasium with like a stick or something like that. If all the kids are running around, then they'll all keep on poking each other with sticks and no one's going to be able to move anywhere. But if you force some of them to go and stick on the side of the wall, then the rest of the people have more room to play. Or dancers or things like that. The same idea. But the thing to remember about fluids, dense fluids, is that there's a lot of molecules. It would be a fun exercise to calculate how many students would have to be in this room to match the same density as like a liquid, for example. I bet it's a lot. Okay, that was a side tangent, but I think it's a really important conceptual thing to understand, that it's not always just the enthalpy that is causing these non-ideal systems. So let's go back to where we were, looking at the Gibbs free energy of a mixture as a combination of its enthalpy plus ideal entropy of mixing. And recall that our reference states were the pure components. So this G of mixture is the same thing as the delta G of mixture. The H of the mixture is the same thing as the delta H of the mixture. And then obviously this is the entropy of mixing. So we're going to evaluate the criteria. Under what conditions does our Gibbs free energy go through inflection points? And once we go through an inflection point, then we know that we're going to phase separate. So if you're going to derive a generalizable equation for a particular mixing model, this is the approach that you'll take to determine what is the binodal, what is the spinodal, and all those different things. And so mathematically, we went through it graphically. Mathematically, this is how you do it arithmetically. So if we do the first step, I'm not showing the calculus, but it's essentially the same thing that we've seen before. In the case xi ln of xi, right, you would have to use the product rule. First times derivative of second, second times derivative of first. Just so happens that x cancels with 1 over x. And in the case of x2 here, right, dx2 dx1 is equal to minus 1. So that's the shorthand of what we got there. Now we do the derivative again. So it is very clear that that quantity is always going to be greater than 0. For the x2, it'll be a plus. Because remember, we're taking the derivative with respect to x1. But that's x2, so we have to have a minus sign, throw it back in there. So we can clearly see here that based on ideal entropy of mixing, the only way that this can be less than 0 if this is less than 0 it's not the most rigorous way to explain it mathematically, but basically this term here has to be the source pulling everything down, right? You have to have somehow your enthalpy overcoming this tremendous gain in entropy that you get when you mix these dilute systems together. So graphically, what I'd like to do is look at these two terms here. So we're going to look at the zoomed in amount as x. So as x1 goes to 0 is what we're going to look at here. x1. What we have is that dg over dx1 minus And this is the limit as x1 goes to 0. So, sorry, this is evaluated x1 equals 0. Right, so we want to look at what is the slope of this curve as it approaches. So if we plug in the numbers here, the ln of x1, 0, this goes to minus infinity. As x1 goes to 0, x2 goes to 1, so this term goes to 0. So what's happening with our G mixing curve here, is that the slope here is negative infinity slope. So in ideal mixing, the entropy approaches the dilute scenario with a vertical line. So if, for example, we were to design a system that was not ever miscible, it would have to be a case where the Gibbs free energy immediately goes up. This would be an immiscible system. So now what we have to determine is this ever possible? So what we're going to do is instead we're going to see under what circumstances can we get this orange line to exist, right? Because if we were to make up a composition here, in the ideal mixing case, our Gibbs free energy is lowered. That means that they're going to mix. In the non-ideal case, the Gibbs free energy increases, right? If you have a higher Gibbs free energy, that would mean that the lowest Gibbs free energy is to just not mix them together. So if you're lowering your Gibbs, that means you're always going to be miscible. If your Gibbs free energy is higher, that means it's a lower energy state to unmix. And that's how we're determining the liquid-liquid equilibrium, and we did graphically. So the only way that this is possible, is this essentially you have an infinite amount of energy that is necessary to mix these two things together. So the only way that you can have a system that is completely 100% immiscible is if I have, in the case we had those orange and red balls in the previous scenario, if I have a sea of these orange molecules, and I want to add in just one red molecule. If that takes anything less than an infinite amount of energy, you can do it. So no matter what happens in the real world, every curve will always have some little dip in Gibbs free energy as a function of x1 as you mix things together. No matter what, it will always have that teeny little dip there, so that everything is at least partially miscible in everything else. Because the alternative is that you have to have two compounds that are so repulsed by one another that it takes an infinite amount of energy to squeeze them and touch. So the whole reason why we have partial fugacity defined is to avoid this problem. Because even in the ideal systems, right, this line here, we approach the dilute scenario with an infinite slope. So instead of worrying about what is the actual Gibbs free energy of the system, we will really care more about what is the deviation from the ideal Gibbs free energy of the system. Because if it's ideal, we know it's infinitely miscible. If it's non-ideal, well, then we've got something interesting going on. But we still know that we've got this infinite negative slope to deal with at the dilute conditions. And this is mirrored, of course, on the other side as well, as x1 goes to 1 and you're adding in x2 to the system. So the whole point of fugacity is to avoid this mathematical complication. And so what's really going on, if we think of things sort of as a enthalpy doesn't want to mix and entropy does want to mix, then all the phase behavior comes from the imbalance of those two. So we really don't care about the ideal scenario, because we know the ideal scenario always mixes. So we just need to know, does the excess Gibbs of the mixture, is that sufficiently high as to prevent these two things from mixing? So everything is lumped into the activity coefficient. So once your activity coefficient gets far enough away from 1, then you can start worrying about what's going to happen in terms of the non-ideal mixing behaviors. Okay, any questions on that? Kind of a recap there. It was a very long recap. But this is really what I think some of the most important parts of the class are, is just making sure that we all have a good, solid, foundational understanding of what are the concepts that thermodynamics tries to accomplish. The details, you can look up the details. If you've got a good thermo textbook, you can relearn how it behaves. But the concepts are much, much harder to learn. Thermo itself in practice is just, what model do I want to use for what compound, what assumptions do I want to make, and then just crunch the numbers. But if we're not quite sure what each number means or how to apply it, then it gets much more difficult. But if we conceptually understand what's going on, everything is just a matter of plug and chug. Choose your model, choose your assumptions, crunch the numbers, calculate the fugacities, calculate the mole fractions. That's thermodynamics. It's just sort of a grab whatever models you want. Okay, so what we're going to talk about for the last little bit of class is a predictive activity coefficient model called regular solution theory. So we're going to skip over the math to some extent. But regular solution theory, we are going to make two assumptions. The first assumption is that it's a binary mixture. Oops. And we're going to say that the molecules are fairly similar, which allows us to make some approximations later on. And two, that the van der Waals equation of state applies. And this theory was proposed by an individual named Van Laar, who was a student of van der Waals. I guess that's probably Dutch or something. So from these two assumptions, we're going to make the mathematical simplifications that the delta V of mixing, which is also the excess volume, is equal to 0, and that the delta S of mixing is ideal, or to put it more conveniently, the excess entropy of mixing is equal to 0. So with these approximations, the Gibbs free energy, that is the excess Gibbs free energy, which is really all we care about in terms of phase behavior, is equal to the excess U, excess PV, minus TS, which means that it all simplifies just down to this, right? This goes to 0, this goes to 0. Okay, U, the internal energy, is a state function. So what we get to do when we mix these two things together, molecules type 1 and type 2, or A and B, we get to choose how we mix them. And so how we're going to mix them in regular solution theory is in 3 steps. We're first going to vaporize pure component 1 and pure component 2 to the ideal gas state. We're going to mix the ideal gases together. Recall that the excess internal energy or excess enthalpy or excess volume of mixing for an ideal gas is always going to be 0. And then lastly, we are going to isothermally compress. So in this case, the excess Gibbs free energy is what we're going to use to build our activity coefficient model. Based on our assumptions, we know that that is strictly just the excess internal energy, which is just going to be our delta U's of these 3 steps, of which we know that the middle step here is already 0. The first step only concerns ourselves with an ideal mixture, and the final step is where we deal with compressing a real mixture. Okay, so how we're going to apply this is we've assumed the van der Waals equation state is valid, so we can calculate the change in internal energy with respect to its volume change. We're either pressurizing it or changing its specific volume. This is an expression that we've seen plenty of times before, and I believe this is the one that we had on the exam as well. So if we crunch the numbers, right, we know that P is equal to RT over V minus B. So if we evaluate this expression for the van der Waals equation of state, we should get a familiar conclusion. So what we need to do to evaluate this, and we're a bit short on time, so I will kind of not go through the details too much, but we can write out that the excess Gibbs of energy is N times G excess Same thing that we've done previously, where we're calculating state changes. We are isothermally just changing the specific volume of our fluid following the van der Waals equation of state. We're adding in those 3 contributions, so just want to highlight a couple differences. This first term here is dealing with pure component 1 being expanded to an ideal gas state, which I believe is the exact opposite of what we did on the exam. Right, we went from an ideal gas state and pressurized it to a particular specific volume and determined how much internal energy changed. The second term here is the same concept, but for the component 2. And the last one is for the mixture, pressurizing it to the final state. Right, we get to choose how we do these mixtures. Okay, so when we evaluate this expression, We're going to make one additional simplification here. We are going to substitute in that the specific volume is equal to the excluded volume. Now, for a liquid, this is probably not too unreasonable, right? Like I said, liquids are extremely dense. So basically, there's hardly any room for the molecules to wiggle around in. So to make this more generalizable, we can just use the excluded volume as an estimate of our liquid specific volume. Just to sort of wrap this up, we have our mixing rules. We're going to make one other approximation. We are going to say that this is equal to 1, just to simplify things down quite a bit.
Are we saying that the whole term in there, that 1 minus kij is 1, or
just the kij is equal to 1? Okay, so now we have an equation for our excess Gibbs as a function of known properties that are tuned based on their pure material properties following the van der Waals equation of state. We can extract the activity coefficient because it is equal to the partial excess Gibbs free energy, which is defined as how does the total excess Gibbs free energy change as I add or subtract a little bit of component I. So just as what we did in the homework that was due on Wednesday with the mixing rules, evaluating the dP dNi, same exact concept, except you're evaluating dG dNi with the infinite summations and all that fun stuff. What we get out of this is the following expression. That should also look familiar. Oops, this is one. This is the Van Laar activity coefficient model. If it follows regular solution behavior, we have this. So instead of using alpha and beta that are calculated based on the van der Waals equation of state, so this is based on the van der Waals equation of state, what is typically done is we just fit alpha and beta. So we can use the theoretical foundation of that form of the activity coefficient model. Again, these activity coefficient models are not just pulled out of thin air. There's some basis generally for why they're written out a particular way. The Van Laar model happens to follow this regular solution theory approach. But instead of trying to predict the coefficients, it's more accurate if we can just experimentally fit them. Now, one other last concept that I wanted to get across before I run out of material is that we can actually improve this in one additional way. So instead of relying on the van der Waals equation of state to calculate these properties, right, we could use that form of the Van Laar equation to tune everything at the end. But we could also, instead of tuning it, insert more real data. So if we put in real data for the delta U of vaporization, this could be for component 1, for component 2, or for the mixture, we can still have a model that might be slightly more accurate and still fully predictive. We'll use an empirical mixing rule where the delta vaporization of U of the mixture is related to some sort of a weighted average of the pure species delta U's of vaporization. We will define, I think this is capital iota. We'll define this as the volume fraction xi e underbar. We'll define this term called the solubility parameter, this delta. And basically, if we take all this information and slap it together, following the similar approach, we can come up with our new activity coefficient model. And this is a fully predictive activity coefficient model. So what this tells us is that our activity coefficient will go to 1 if the solubility parameter of component 1 is equal to the same thing as the solubility parameter of component 2. So this is a very common first pass approximation mixing sort of model. So regular solution theory is used very commonly in a lot of different disciplines, especially in our research area looking at heavy hydrocarbons. Because if you don't necessarily know all the properties, you can maybe just tune what the activity coefficients, what the solubility parameters would have to be.
What is the name of this model?
This is all falls sort of into regular solution theory. Different sort of approximations of regular solution theory. So, if we just take one more quick conceptual second to think about this model, what effectively we're saying is that we have a mixture here that probably follows some Leonard-Jones interaction. So if this is the U in terms of the potential energy between two different molecules, separated by some distance Rij, this is common nomenclature that we'll be more familiar with starting sort of next week. What this is basically saying is that the solubility parameter, right, is the delta U of vaporization. So if we take a compound that's sitting right here in its nice, happy potential energy minimum well, and we pull it apart to an infinite separation distance, that's effectively what we're saying is this step of delta U of vaporization to the ideal gas state. So what this solubility parameter basically says is if I take two molecules and I stretch them apart, it takes a certain amount of energy to stretch them an infinitely far distance apart. If two molecules have similar amounts of energy that is necessary to rip them apart completely, then they're probably pretty similar in structure, composition, and behavior. And that means that your activity coefficient is going to be likely equal to 1. So that's sort of the conceptual foundation behind regular solution theory. Right? Because if they're curved here, if they're very similar, well, then maybe you'd expect them to mix pretty well. Right? So that's a way that you can relate sort of the molecular scale interactions to the large scale macroscopic phase behavior. So regular solution theory is a fully predictive model, but we still need to insert in a little bit of experimental data, namely the solubility parameter, which is tabulated for most all compounds. And if it's not, you can fit it. But in terms of liquid-liquid phase equilibrium, vapor-liquid phase equilibrium, start with the fugacities, determine your models, crunch the numbers. Right? So your goals of phase equilibrium calculations are 1, calculate your fugacities, use those fugacities to calculate your mole fractions, use those mole fractions to perform immaterial balance. All phase equilibrium calculations are effectively the same thing. But the differences all come into what models do you assume, what approximations do you want to make, and how do you want to go about solving the problems. So just like with the bubble pressure or the bubble temperature or the dew point or the flash conditions or the distillation, every single one of those equations was using the exact same set of Raoult's laws assumptions. But there's so many different ways that you can manipulate them together. So you've got to feel comfortable with those for sure. And so these are for non-ideal systems. Okay, any questions before we break for the weekend? All right, have fun.